Hello, everybody, and welcome to today's session. My name is Shane Hawthorne, and I'm the Senior Manager, Aerospace Technical Leader at Amazon Web Services. And I'm joined here today by Dan Sepperly, who is the co-founder and CEO of an exciting company named Leo Labs. And we're here today to talk to you about how to accelerate space traffic management in the cloud. This is like a really exciting session for me to actually work on because I've worked on a lot of cool projects at AWS, but this one actually goes back to my own background and experience of when I was a captain in the U.S. Air Force and I worked at Cheyenne Mountain. And in those days, we were monitoring everything in space. We've always monitored everything in space. Not as much as like you see these guys with the telescopes on the upper left-hand corner. But when I was at Cheyenne Mountain, we still had the Mir space station that was being flown by Russia in orbit around the Earth. And we were tracking debris and satellites to make sure that it didn't hit the Mir and that it didn't hit the U.S. space shuttle. And why did we do that? Because we wanted to let the command center, as it was called, in the upper right-hand corner, know if there was anything that could endanger space travel, and we needed to alert them. But the funny thing was we did that with significant infrastructure. If you look in the upper left-hand corner, you'll notice what we called lovingly the 427M. And that was the computer system that I actually used when I started there as the head of Astro. And if you look in the middle, you'll notice it was all done on a massive on-prem computer system that literally took up a room about the size of a football or half of a football field. And it rendered incredibly beautiful graphics, as you could see in the upper right-hand corner, with a CRT type of display showing us orbits and things that we were going to have to worry about monitoring up in space. But this has been going on, and it continues even today to grow. With the growth of proliferated LEO constellations and more people launching satellites into what we call LEO, low Earth orbit, we've got thousands of objects out there, and it's growing more and more every year. And we now use a system, still quite old, that feeds it called the SPADOC 4C, which also does collision avoidance. And what's crazy is when we used to do these runs, we were only able to do a couple of satellites versus a couple of other satellites. And it would literally take so long for us to do this that we would go to lunch during the run and come back, it still wouldn't be done, and it would continue operating. And literally like 4 or 5 hours later, this collision avoidance activity, which would tell us if two satellites were going to come close to each other, would end up finishing, and then we would know. And if we had some need to like maybe update a satellite's location or make it a little bit more precise, we would then end up having to run it again. And 4 hours later, it would get done. So the cool thing about Leo Labs and what Dan is going to talk to you about today is how they've been able to use AWS to revolutionize how they do collision avoidance and then how you can do space traffic management in the cloud. So I'm really excited that Dan's here today, and over to you, Dan.
Shane, thank you for that great introduction. It's an absolute pleasure to be here. And today I want to spend some time talking about our collision avoidance service, which is run off of our global radar network and off of the platform that we have running in the AWS cloud. So why are we even talking about space and low Earth orbit? Well, space is going through a once-in-a-generation revolution, and it's a business revolution. The cost to launch and build and operate satellites has come down an order of magnitude. And it means that there's thousands, even tens of thousands of new satellites headed to space, and they're delivering innovative new applications around the world. So mapping services like the images you see in mapping applications, and airplane and ship tracking, and soon broadband internet access are all delivered by satellites and fleets of satellites in low Earth orbit. So low Earth orbit is being filled with critical assets for businesses around the world. On top of that, there's already a significant number of satellites, and for the purposes of this conversation, space debris that threaten those satellites. So the numbers are quite important. There's about 14,000 pieces of space debris tracked today, and there's about 250,000 pieces of small debris that are not tracked but threaten satellites. So that debris and that new satellite traffic is critical for the space industry, and the scaling in those numbers is the reason we're here today talking about this topic. So, what is LEO Labs? Well, LEO Labs is the commercial platform for space traffic safety and space domain awareness. There's a data deficit in low Earth orbit, basically a lack of information about what satellites are doing and what the space debris risk really is. So LEO Labs has two technological foundations: a network of radars to track those satellites and debris, and an online software platform to turn that information into alerts and information to help satellite operators in the broader space industry operate smoothly and safely. LEO Labs is a startup based on 20 years of R&D, specifically research into advanced radar systems and satellite operations technologies. We actually got our start in the scientific community tracking the Aurora Borealis in the Northern Lights. It turns out those scientists, when they were collecting their data, found that there were satellites and space debris in the data, and it was noise to them. So they spent years writing software to identify that information and throw it away. We turned that around, kept the satellite data, and turned it into an always-on service that is the foundation of LEO Labs today. So we're a horizontal service provider. We deliver services to the satellite operators, regulators, defense organizations, and the insurance industry. So I wanted to turn just to our technology for a moment. The first piece of our technology is our global radar network. We operate radars like the ones you see on the screen here, and we operate them around the clock to track satellites and space debris. We use radar because it can operate around the clock. It's not affected by weather, it's not affected by clouds, it's not affected by sunlight. In addition, we use a type of radars called phased array. It means no moving parts. Instead, every millisecond, we're able to electronically steer from one satellite to another to a piece of debris. And that's critical because we're tracking thousands of satellites and pieces of debris per hour. We're quite proud of the radars that you see here because we're able to build them very quickly. Each of these radars was built in less than a year. That's a year from breaking ground to delivering data. So we're in the process now of expanding this global radar network. Turns out if you have only one radar, you really can't do a good job of tracking the satellites or the debris and providing collision warning services. So with a network of 6 radars, which is what we're building to over the course of the next year, we'll be able to provide information services in 4 hours or less on high-risk situations like conjunctions or new launches. We also now provide a coverage from the Southern Hemisphere. And we're quite proud that the Kiwi Space Radar is the first radar of its type in the Southern Hemisphere. And we'll be able to track all the small objects. So we got the 3 radar sites today in operations. And if you look at the map on the left side of the screen, the red areas show the portions of the sky that those radars are monitoring. So we've got the radar in New Zealand, the radar in Texas, and a radar site in Alaska. We'll have 6 radars by early 2022. We've got the site in Costa Rica under construction. And then there's 2 more sites on our map. They're just notional. We're not disclosing the locations yet, but we'll have announcements soon. Even with the 3 radars, we're actually able to produce a large amount of service, a lot of data today that is going out to customers. So we take over 500,000 radar measurements every single day. That's over 500,000 measurements on the satellites and on the space debris. We update our estimates of their orbits, the trajectories they're on for the next 7 days, over 13,000 times per day. And we're producing over 800,000 conjunction alerts. And conjunction is the term the industry uses for potential collision or risky situation. And for any high interest events or high interest satellites, we're able to revisit those, check in on them up to 6 times per day. So this is the foundational data set that ultimately drives the collision avoidance service that we'll be talking about here in just a second. The other big technological piece of the business is our SaaS platform. So this is the software system that lives in the AWS cloud that provides the real-time services. It processes the data in real time as it flows off the radar network, and it responds to customer requests in real time. So on this diagram on the left, we have the radar network continually flowing information up to the cloud. In the middle is a very rough outline of the architecture of our systems, where we have a set of databases that store the information we have, essentially making us a DVR for space and giving us the ability to rewind and replay any incidents that are detected. We've got a set of analytics tools and packages that are continuously and automatically scanning the data stream to look for important events and flag those for users. And then we have the interfaces with the users. So on the right side is our API and our GUI, the dashboards that we produce. Through the API is how we deliver all of the alerts and the information that is streaming out to the customers. And this is especially critical because these days the satellite fleets are so large that they use automated procedures to fly their satellites. And the people only get involved for very special events or to handle, say, new satellites that are being introduced into the fleet. So most of our customer interactions are with the computer systems that manage their assets. But then we do have a set of dashboards and displays that I'll show you in a second, where our human users can get real-time information about a situation, or they can get reports about the situations that they care about. And then, of course, off to the right side are all the users of this data, and it ranges from space agencies to satellite operators to the insurance industry. So, collision avoidance is the topic we're going to dig into today, and we need to start with the big question of why is collision avoidance even an issue? Well, it turns out that when there's a collision in space, it not only damages or destroys an individual satellite, but it produces a set of debris that can stay in orbit for years or even decades. And then that debris can go off and threaten other satellites in the same constellation or other constellations. And these collisions can have quite an impact. So if you look at the plot on the lower right here, this is an interesting plot from the European Space Agency. And it shows every single year how many new objects were created in space. And you can see there's kind of a steady introduction of new objects over the last few decades, many from new launches and satellites that were put into space. But there's a few spikes off to the right side. The middle one, labeled the Iridium Cosmos collision, was the biggest collision to date between a defunct satellite and an active commercial satellite. And it created 2,500 pieces of debris, many of which are still in orbit today. So in an instant, there was an additional 2,000 or more pieces of debris circulating up there that other satellites had to avoid. A couple years before, there was actually a weapons test that produced over 3,000 pieces of debris, that many of which are still in orbit. And then you can see, maybe on a more positive note, the picture on the right, the launch of new satellites over the last few years. This is the new space revolution that contains lots of new functional satellites that are delivering innovative new services. These are the services and satellites that we want to protect. So people also often ask, well, with collision avoidance, is the possibility just to keep an eye on it and then swerve at the last second to avoid a collision? Well, unfortunately, the way space works, things are moving way too fast for that to happen. So if you're in orbit, if you're in low Earth orbit, you're moving at about 8 kilometers per second, or 17,000 miles per hour. And so that means that anything that's close to you and is going to whiz past is going to be past you fast in the blink of an eye. So when we talk about collision avoidance, we actually talk about predicting up to 7 days into the future to let a satellite operator know that there's going to be a risky close approach. To put it in another context, we're basically predicting hundreds of laps around the Earth into the future to let people know that there's going to be a narrow miss or a potential collision between two objects. So I want to zoom in now in particular and show you how the conjunction of the geometry of a conjunction shapes up. And in particular, I'm going to show you a conjunction that we were watching in about a year ago in early 2020. These are two defunct satellites, a telescope that was launched in the early 1980s, and a experimental satellite that was launched back in the 60s that had been orbiting up there for a long time. When you look at the lower right here, you're going to see a movie that was created by our system as it monitored this conjunction. This particular movie shows the two objects as they approached one another and then flew past one another. And I'm happy to report that in this case, it was a miss. We didn't have a collision. In this particular movie, you see and there they went, the two objects just passed one another. The green line and the orange line are the paths that the two objects are on. And the ovals or the ellipses are the regions of space where the satellites are located. So we take our radar data and we turn it into predictions of exactly where those satellites are going to be. No prediction can be 100% perfect. So a big part of our business is fitting or determining the error bars around our measurements and around the satellites. And that's what those ellipses represent. That red area is the region of maximum overlap, or the most likely location of a collision. And you can see in this particular case, the two objects came very close. In the upper right corner is the miss distance. They missed by just about 40 meters, or closer than football field. And in the lower right, you can see they were traveling about 14.7 kilometers per second relative to one another. Now, spinning the screen around, you can see that the two satellites missed slightly in altitude. One passed slightly above the other, which was fortunate and meant that we didn't actually have a collision in this scenario. So this is one particular conjunction, one particular close approach. So then the question becomes, how often does this happen? Well, if you look at the right side of this screen, you see a display that we launched in May 2020 when we launched our collision avoidance service. This particular display shows all of the conjunctions that we're tracking over a 7-day period. So these are all the near misses occurring in low Earth orbit. Each red dot represents two objects flying close to one another. And I'm going to play a movie here briefly. You can take a look at all of the different conjunctions that we're tracking around the world. So you can see they're kind of spread all over the place here. But there's actually some regions of the world where there's more likely to be collisions. If you look up near the poles, so close to the North Pole and close to the South Pole, there's actually some pinch points because most of the satellites that have been launched into space are in polar orbits. And so where these pinch points are located is more likely to have debris and satellites flying close to one another. Now, another aspect of this display, we can actually zoom in to look at conjunctions with varying levels of risk. So there's a lot of close approaches here, but what the industry has converged on is when the risk reaches about 1 in 10,000 or 1 in 1,000 level, they will take action. They will move a satellite. So if we zoom in on those actionable conjunctions, you can see that there's a number of those on the order of 10 to 20 that we're tracking around the world right now. And those are distributed all over and represent near misses or potential collisions. When active satellites are involved, there's the opportunity to actually move the satellite. But unfortunately, there's a significant number of these where there's two dead satellites involved, or a piece of debris and a rocket body. And in that situation, there's currently nothing we can do about these conjunctions. However, in the future, we're very hopeful that there'll be this active debris removal industry that'll be launched to go up, grab those satellites, and get them out of the way. So the service that we have here has a number of features to it. We're able to, every time we get an update on a satellite or a piece of debris, send out a new conjunction data message, let our customers know how the conjunction is shaping up and whether they need to move their satellites. We also have the ability to take the maneuver plans for the satellite and check those. So if you're going to move your satellite, you want to make sure you're not moving into a different collision. And we've got the ability to, within seconds, screen a satellite against the entire catalog and get answers back to the satellite operator. And that's something that AWS and the cloud platform has been critical for, making that instantaneous, making the response and the search capability move very quickly. And then in addition, we provide a lot of supporting metrics and data about the service levels and the quality of service that we're providing. So we're quite proud of this. It's the first modern CA service that's responsive and provides reports that can be used not only by the satellite operator, but stakeholders like company management, regulators, and other satellite operators that may be involved in some of these situations. So I want to talk just a little bit about some of the future of space traffic safety as well. Another part of the industry that is starting to take shape is the satellite servicing and the active debris removal industry. So in that industry, they build and launch satellites that fly into space and go up and get close to another satellite in order to fix it or to refuel it, or if it's a piece of debris, to ultimately tow it down into the atmosphere and burn it up, so that it is no longer a risk to other satellites in LEO. This is an industry that's just starting. It's going through some proof of concept missions right now, but I think it's going to be an incredible tool for the entire industry moving forward. And so we have a tool called a proximity operations tool that enables navigation for these satellites. It basically shows what satellites can be serviced and how to get to those other satellites. So if you look at the screenshot on the right side here, you'll see one satellite highlighted in blue, which is the servicing satellite. In the future will be the servicing satellite we're talking about. And then the other orange balls are the satellites that can potentially be serviced by this particular satellite. So this satellite will be able to move and drift over to another satellite to eventually dock with that satellite. And you see on the right side some relative motion plots. It basically shows how this one satellite is orbiting relative to another satellite. Things often look kind of simple at the macro level. So if you look at the globe, it kind of looks like, well, the satellites are just on a circular path around the Earth. But actually, when you look at two satellites relative to one another, it starts to get more complex. Each satellite's in a slightly different orbit, and being able to navigate in and dock with the satellite is actually quite tricky. And that's where these navigation tools are going to become quite important. And finally, one other thing I want to highlight is we focus a lot on launch and early operations. So when these satellites are launched into space, they're often traveling up there with a bunch of other satellites on the same rocket. We just supported the Transporter-1 mission, which had a record-setting 143 satellites on the same launch. And it's critical to track those satellites very quickly so that they can be rapidly brought into operation and safely maneuvered out of the pack and off into the orbit that they need to be in. The data that you see on the right side of the screen here shows some of the first radar data that we collected on that Transporter-1 launch. Each one of those slashes represents a separate satellite that was deployed into space. And across the horizontal axis, you can see we've got time in seconds. So basically, over the course of 30 seconds, we saw a pack of satellites fly past one of our radars, and we were able to turn that data into predictions about where those satellites would be, so that the satellite operators could point their antennas, get in touch with their satellites, and move them into operations. And I'm quite proud to say that that entire deployment went quite smoothly. And so this basically represents just the start of these satellites' multi-year missions, and just the beginning of their work on space traffic safety and collision avoidance. So I want to dig in just a little bit on, kind of pull back the curtains and look a little bit deeper into the LEO Lab system. You see here a diagram of the system that we're running in the AWS cloud, and give you a little bit of sense of the services that we're talking about. So when we talk about collision avoidance, we may be focused on a single satellite. We're actually talking about being able to check that satellite and its trajectory against 16,000 other satellites or pieces of debris today. And in the course of the next couple of years, being able to check that satellite's trajectory against up to 250,000 other satellites and pieces of debris. This is a task that frankly used to be impossible because we weren't able to scale up the computing resources to be able to do that in any sort of reasonable amount of time. But now that we're working in the cloud, we're able to put that data into the cloud in real time, and we're able to conduct those searches in real time. So we've got a back-end system that's got a set of databases that rely on the Amazon RDS service and also the Amazon S3 service as well to store and move the data. We also use the Amazon HPC system in order to process that data quite quickly. And we've got a set of analytics tools you see here marked as conjunctions and marked as orbit determination that are able to sift through that vast amount of data very quickly and get responses and alerts off to customers fast. Then over on the front end side, we've got a set of tools that are supporting the API and ultimately our online dashboards, and are able to scale up as we have more users logging in and connecting to the system. One other thing that's important here is the different customers like to interact with the system in different ways. They need data on different cadences, different formats, and the like. And we've got a set of customer integration apps that connect our specific services over to the systems that are flying their satellites. So it's ultimately this system and this AWS cloud architecture that enables us to scale up as the satellite industry scales up. And to reiterate a point from earlier, there's about 2,000 functional satellites today, but there'll be about 50,000 functional satellites in the next 3 to 5 years. So we're expecting to see the workload grow dramatically simply by the new launches. But we're also expecting the workload to go up because we're going to be shifting from tracking 14,000 pieces of debris to tracking 250,000 pieces of debris over the next couple of years as well. So, all of this is summarized, this performance information is summarized in a system metrics page that we maintain. Our system automatically reports these numbers and reports them in real time. Some really important numbers in terms of an actionable automated system. Our system's able to go from a radar pass that is collecting data as the satellite flies over the radar to delivering that information to our customers in 10 minutes. And that's truly amazing because that means that the satellite may be on the far side of the world and we're able to run that radar, get that data up to the cloud, and then get it off to the satellite operator who is located continents away in 10 minutes. The processing time reductions have also been truly remarkable too. As Shane mentioned, conjunction assessment used to be a very manual process. It used to be done on 8-hour shifts with a lot of human intervention. We are now able to process a customer request in a handful of seconds and basically speed up the process by 99.9%. And this means that a satellite operator, can now sit in a conference room during a meeting and iterate on their satellite navigation plans. And by the end of the meeting, have a solid plan of action to prevent a collision and also be able to continue their satellite mission, whether it's collecting imagery, providing communication services, or the like. And we're delivering a lot of these messages every single day. So our system is actually producing 181 million conjunction data messages, essentially collision alerts, every single month. So all this data streaming in is being analyzed in real time and turned into these alerts. And we're able to, right now we're supporting 46,000 maneuver checks per month. So these are satellite operators verifying that their maneuvers, their satellite plans are going to be safe. So with that, I'd really like to thank Shane for the opportunity to speak here. We've been scaling up rapidly with more radars, with more services for satellite operators, and the AWS system has been critical in enabling us to scale. If you'd like to see the last 24 hours of space, I invite you to go to the link here. That display I showed you on the first slide with all the satellites and debris flying around the Earth is available just to the open web. So you can go to this link, spin the globe around, look for your favorite satellite, and basically keep an eye on space. So with that, I'd like to say thanks again, and back to you, Shane.
Wow, Dan, that was great, and thank you. Everybody, I just wanted to add some key takeaways for you to get from Dan's great discussion, and that is that cloud computing really does enable orbital safety. As you can see from Dan's discussion, low Earth orbit is busy and changing fast, and that's because they're actually using AWS's scalability and high-performance computing to enable them to track over 20 times more objects than back in the dinosaur days when I was out there predicting collisions and helping keep people safe in space at Cheyenne Mountain. Leo Labs actually used AWS to do something that's really incredible. They deliver a 99.9% reduction in computation time, which is that's just fantastic. So the days are gone of where you could go do a collision avoidance run and go eat dinner like I did. Now you actually got to be ready to do something really fast. And that allows them to support satellite operators, regulators, and the defense world because they have to watch over space. It's moving from 14,000 objects to over 250,000 objects, an exponential computational growth required to keep up with that. So, Dan, thank you for telling that story and showing everybody how we do that. I also wanted to cue everybody to know that if you want to learn more about AWS, Aerospace and Satellite Solutions, Ground Station, or about what we're doing in space, here's some great links for you guys to go look at. And finally, if you want to get as good with AWS as Dan and Leo Labs is, we have a great training and certification program going that you can get to at aws.com/training. And then you guys could pick up these skills as well. So thank you, Dan. Thank you, Leo Labs. And everybody enjoy the rest of your sessions.